Now, with the knowledge of the sequences and then the bounded sequences, unbounded sequences, bounded sequence, then we are going to go for the least upper bound. It is called a supremum and the greatest square bound of the sequence. It is called the infimum that we have to see here. Okay. Now, least upper bound or supremum means you see the definition. A real number m is said to be the least upper bound. A real number m is said to be the least upper bound or a supremum of sequence n. Whenever you are writing a sequence in the sense you have to write an in the four brackets. An is the end term of the sequence and you have to write that in the four brackets. That indicates that is a sequence. Okay. Now the condition there are two conditions are there. The first one is M is the upper bound of sequence An. Okay, you see here one of you see here. One is M is the upper bound of the sequence An. That means already you are taken that the definition. You see upper bound in the sense An is equal to M. If it is a lower bound, you are already know An greater than or equal to M you are getting. But here you are writing upper bound means An less than or equal to M for every n belongs to n. This is understood n belongs to n. That is the set of natural numbers that are going to get for the small value of n. Okay, and here you have to substitute the values n equal to 1, 2, 3, so on. N equal to 1, 2, 3, so on. Now, the second condition is any number less than m cannot be a upper bound of sequence an. That means to see if a epsilon greater than 0 is existing, then there will be a term ak such that ak greater than m minus epsilon we are going to get here. You see here an or ak, whatever it may be here, you see ak greater than m minus epsilon. That means any number that is less than m cannot be a upper bound of that we are writing here. Okay, any number less than m cannot be upper bound of sequence A, and that means whatever number you are taking, that, that must be not less than m. Number less than m cannot be the upper bound of sequence A. And now you see the second definition is the infimum. A real number m is said to be the greatest lower bound or infimum of the sequence A. And if m is the lower bound of the sequence, already I am told to you, you see after seeing the previous classes, that is lower bound in the sense A n greater or equal to m. You see, don't bother about smaller m, capital M. Okay, if you write near the capital M, you write capital M. If you write small letter M, small letter M. Just to concentrate on this. It is less than or equal to or greater than or equal to. Lower bound means according to the definition, you can write A n greater than or equal to M. A n greater than or equal to M, you can write. Now, here if you see the definition, the first one is M is the lower bound of the sequence. That is, this is according to the definition of writing here for every n belongs to n. Okay, for every n belongs to n. Now, to the second one here, you are writing any number greater than m cannot be the lower bound of sequence. Just to remember here, how you have to remember means to see. Already I'm told to you, less than, greater than, or equal to. Those three you take here. Greater than or equal to is there. If you three inequalities, if you take what is the remaining one that is equal to, less than is there. The less than you are writing here. In the previous case also you see here, en less than or equal to m is there. I am already told you. Remember less than, greater than, or equal to. Okay, here you see a less than or equal to m is there. Now the remaining equality out of the three is you are getting here greater than you are getting. You see here ak greater than m minus epsilon. That is the way you have to remember. Okay, here also a greater than or equal to m is there. That is the third one is less than is not there. That you are writing here is the next condition ak less than m plus epsilon. This is you are writing. That is the way you have to remember. Okay, that is number greater than m cannot be lower bound of sequence a n. Okay. Now we will see some of the examples. You see in the order taken in the previous some of the as you see here examples 1 by n, that is a sequence an equal to, we are adding sequence 1 by n. That means an equal to 1 by n. An means the nth term we are adding 1 by n equal to what we have to say already you know. Small letter n belongs to the capital letter n. That is the natural numbers. The natural numbers are 1, 2, 3, 4. So on you are getting here. You put n equal to 1, you are getting here 1 by 1, that is equal to 1. That is a1 equal to 1 you are getting. A2 means you have to write A2 equal to 1 by 2 you are getting here. Right? You have to replace n by 2. 1 by n means 1 by 2, that is equal to 1 by 2. Similarly, the remaining thing you are adding. Now, if this is by observation or by inspection you are adding this. That is the supremum of the sequence is 1 and the infimum is 0. Okay. That means any number if you take, that is every number is less than or equal to 1. But this is here you see the infimum is 0. Any number if you take is greater than 0 is existing. That's why you are adding here. Any number greater than 0 means that is infimum is the lower one and the supremum of the lower sequence is 1. That means whatever you know that is an you are taking here, that is less than 1 you are getting. Less than or equal to 1 you are getting. That's why you are adding here. Supremum is 1, infimum is 0. Similarly, the remaining thing you are adding. The second one you see here, 1 plus 1 by n. That means an equal to 1 plus 1 by n. Here also the same way. How you have to write? An in the sense a1 equal to a1 means the first term, a2 means the second term, a3 means third term. If you write, already you know the sequence a you are writing here as you are writing here you are writing 1 plus 1 by n equal to 1 plus the a1 you get there. 1 plus 1 by 1 is equal to 1 plus 1 is equal to 2. And then the second one, 1 plus a2 equal to 1 plus 1 by 2 you are getting here. A3 equal to 1 plus 1 by 3 you are getting. But the next one here, a4 equal to 1 plus 1 by 4 you are getting here. That means you see that the supremum is the highest one that is existing here is the 2. Here you see 1 plus 1 by 1 means you can write 1 plus 1 that is equal to 2. That is the maximum that is existing here. Any number if you take that is less than 2 is existing. That's why the supremum of the sequence is you are adding to. Of course, the definition what you are taken less than 2 cannot be a there cannot be the supremum. Okay, the supremum of the sequence is equal to so and whatever you take that is less than the 2 is existing and infimum is 1. Whatever you take that is greater than 1 is existing. 1 plus means greater than 1. Whatever means the remaining value you are adding here, the infimum is 1 you are adding. Similarly, the remaining thing you are adding here. Here also you see minus 1 to the 4 n into 1 by n means you are writing here also the same way an equal to minus 1 to the power n into 1 by n you are writing a1 equal to you can write minus 1 to the power 1 into 1 by 1 you are getting minus 1 1 by 2 minus 1 by 3. So this is a1 a2 a3 a4 again by here you see whatever you take the number is less than 1 by 2 is existing. 1 by 4 is definitely less than 1 by 2. 1 by 2 is the major one. The next one you are going to get minus 1 minus 1 by 5 plus 1 by 6. Whatever may be the remaining values, you see, the highest one is existing here is 1 by 2, remaining are less than 1 by 2. That's why here already the supremum is 1 by 2, and any number less than that is not the supremum. Okay. And then here you see infimum is 1 minus 1 by 1 is any number if you take here that is greater than minus 1 is there, but greater than minus 1 is there, and then here the infimum the lowest number that is existing here is minus 1, you are getting it minus 1 by 3 that is less than that is here you see the condition must be satisfied here what is an greater than that value that is what are taking 1 by 2 cannot be a if you add something that is the supremum you are getting here minus 1 is the supremum here also you see supremum and infimum are 1 and minus 1 because you see highest value is 1 you are getting here so because already the range is equal you are getting here the range is equal you are getting two values minus 1 1 that means here you see the here you see the supremum is 1 and infimum is minus 1. Okay. Supremum is 1, infimum is minus 1. Okay. Now the limit of a sequence. Now the limit of a sequence. Already you know function of x that you are writing the limit of the function you are writing. Is it not? You are studying the limit of a function. Okay, the same way you are writing here limit of a sequence. How you have to take means you see by taking the answer that we are writing this. We just you see the definition here. The sequence an is set to tend to limit L as n tends to infinity if given epsilon is greater than 0. However small, there exists a positive integer m of epsilon. If you have m also, there is no problem here. M is depending on epsilon. So m of epsilon, you see m of epsilon depending upon epsilon such that modulus of a in minus L is less than epsilon for every n that are equal to m of epsilon. So writing here. For every n greater than or equal to m of epsilon. The same you are writing here, limit an as the entire simply equal to L you are writing. Now, of course, here you see how you are writing in case of the limit of the function you are writing limit f of x that extends to a is equal to f of a you are that is equal to some L you are writing. The same way here also you are written the same here. However, there is a positive integer m. There is no need to write m of epsilon here, you can write m also, there is no problem here. modulus of A minus L is less than epsilon for our n greater than or equal to m of epsilon, because we are taking here m of epsilon, and that is denoted by limit E n as n tends to infinity equal to L. In case of polynomials, how you are writing? Limit f of x or x tends to A is equal to L, that you are writing. The same here also you are written. Now you see, already you know modulus of y is less than epsilon means how you are writing? Minus y less than epsilon less than y you are writing. Here also this you are writing, that is the or taking that modulus of A minus L is less than epsilon, you are writing as minus epsilon less than A minus L less than epsilon for every n greater than or equal to m you are writing. The same you see, you add L for all the three components. This one component is another, this is another, three components you add, you get here. Okay, that means the meaning of this is an belongs to the L of L minus epsilon n plus epsilon for every n greater than or equal to m. You can write. This is what I understood already. You know that the same thing you are writing here. Now you see L minus epsilon less than A n less than n plus epsilon means you can add A n belongs to the open interval. Already you know open interval means it doesn't take the boundary values. It takes the in between values. That is in between L minus epsilon and L plus epsilon it will take, but doesn't attain the values of L minus epsilon as well as L plus epsilon. That is, if it is the closed interval, it can get as the boundary values, but here the open interval is there. That's why you are getting here only the values between L minus epsilon and L plus epsilon for every n greater than or equal to m. This is the limit of the sequence. You have to remember this based on that you are doing some of the problems. Okay, that whatever just a n tends to L, whoever small there is the positive integer m of epsilon, such that you are writing here modulus of A minus L less than epsilon, writing for every n greater than or equal to m, limit n as n tends to infinity equal to m means you can write here modulus of A minus L is less than epsilon. It is not. This is so for every n greater than or equal to m, you can write this limit. That you remember here. Well, same you are using in the problems. Okay. Now we'll go for the sequence. The sequence that you see here, the sequence f from n to r. What is the general way of representing the sequence is f from n to r or a from n to r or x from n to r. You can take here f they are taken here. Defined by f of n equal to 1 by n. Already you know f of n in the sense a n equal to 1 by n. The answer is 1 by n here. Okay, has the limit n equal to 0. We will prove this. Just you have to prove this. How you have to prove this means you see for the same definition you are using here, that's why I will say to remember. For every epsilon greater than 0, there exists a positive integer m such that 1 by n minus 0 with modulus is less than epsilon for every n greater than equal to m. This is the case you are writing. You see in the previous case you are written what you are written there. Modulus of n minus L less than epsilon for every n greater than equal to m. If it is so, limit an as n tends to equal to L, then you are writing that. Okay, here an equal to 1 by n is there. Now previous definition you are replacing an by 1 by n, and here L you are replacing by 0. Okay, 1 by n minus 0 with modulus sign for n greater than equal to m. Now here you see, to take n greater than equal to m, if you take the reciprocal, the inequality changes, because whenever you are taken the minus sign or whenever you are taken the reciprocal, the inequality changes. You see here, greater than equal to is there, you are taking the reciprocal. Suppose if you take x is the, if you take some x, the reciprocal of x is 1 by x, you are writing. The same way m is reciprocal means you can write 1 by n, m reciprocal is 1 by m. Okay, here greater than equal to is there, that will become less than or equal to. Okay. Now here just to write here 1 by m less than epsilon if and only if m greater than 1 by epsilon. Here also the same you see, this is here itself you cannot directly, because here you can less than epsilon means you can write 1 by m is less than epsilon. Now if you take reciprocal of this, you can write 1 by 1 by m, that is equal to m, because reciprocal of the reciprocal is the same you are getting here. That means you are writing m greater than, because here you are taking a reciprocal epsilon, you are writing as 1 by epsilon, 1 by 1 by m you are writing as m. Here less than will become greater than, because you are taking the reciprocal. And I'm already told you, whenever you take the reciprocal or negative on both sides, you get the inequality get changes here. Okay. Now for epsilon greater than 0, you can write an integer m greater than 1 by epsilon and use to. Here nothing is there. Just you are writing here. You keep n one side, remaining on the other side, and you write here. Okay. Here you see n is one side, you are getting here 1 by m less than epsilon, 1 by n less than 1 by m less than epsilon. Okay. Here also the same definition you are writing here. By using the definition you are writing here, you see already I'm told you, whenever modulus of a n minus L less than epsilon means you can write limit a n as n tends to equal to L. Here a n equal to 1 by n and L equal to 0. That's why you're writing here limit a n as n tends to equal to L. Here n equal to 0, an equal to 1 by n. That's why you are writing it. Just you are using the definition you are writing. You keep n one side remaining and on the side you write the same here. N you are writing here, the same you can write here. You can get it easily. Okay. Now the second, just you see, just you concentrate on this here. The second one, using the definition of the limit of the, you are not proving anything. Just you are using the definition you are writing here. Okay. Now using the definition of the limit of the sequence, show that limit 3n minus 1 by 4n plus 5 as n tends to infinity equal to 3 by 4. Okay, now you see here solution here the same. Let us according to the definition writing that epsilon greater than 0 be given. We have to show that there exists m such that already you are taken modulus of n minus l less than epsilon for every n greater than equal to m. That means here this thing 3n minus 1 by 4n plus 5 equal to an and 3 by 4 equal to l you are writing. Is it not? You see here, this entire thing is you are writing as an, this you are writing as l. According to the definition, limit an as n times equal to l, that you are taken the limit of a sequence. You see that definition already are taken there. You see here you got to somewhere here limit of a sequence. Here you got the limit an as n times equal to this you got there. Okay, the same you are writing here. Okay, now you see here by applying that by applying that. Here, an minus 3 by 4 with modulus is less than epsilon for every n greater than equal to m. Okay, now the same thing you can write as an you replace here and simplify the expression that is containing under the modulus sign so that you take the LCM and don't simplify the denominator, you keep denominator as it is and simplify the numerator only and you write this, then you are going to get this, that is minus 19 by 4 into 4n plus 5 is modulus sign less than, so remaining is same. Just you write the, don't simplify denominator and simplify only the numerator and you write here and the same modulus sign you are writing here. Okay, already you know this is the minus sign is there. Modulus sign means you can write minus, you can replace by plus, because modulus of minus 1 you can write as 1, modulus of minus 2 you can write as m. That's why here you are writing it as 19 divided with. Now already I'm told to you, you keep n one side remaining on the other side. Okay, now if you cross multiply, here you are going to get 1 by 4n plus 5 less than 4 epsilon 19. Okay, you keep 1 by 4n plus 5 one side, remaining on the other side. We have to get the value of n. Okay, now after getting this value that is less than 4 epsilon by 19, now you take the reciprocal. Whenever you are taking the reciprocal, less than will become greater than. You see, 1 by 1 by means you get here 4n plus 5 you are getting this side, and 1 by means you get here 19 by 4 epsilon and less than will become greater than, because you are taking the reciprocal. Is it not? 1 by 1 by of this, 1 by of this, you are writing less than will become greater than, because you are taking the reciprocal. I'm on to again, I'm saying whenever you are taking the reciprocal, that is or minus sign, the inequality changes. Here you are taking the reciprocal, that's why the inequality is changing by less than by greater than. Okay. Now I'm already told you, you take n one side remaining on the other side. Okay. Here 4n greater than, you write here n greater than, you are going to get this. Okay, now just you replace n by m. Okay, now you replace, choose m such that m greater, just you here you replace n by m greater than so and so, then you write the definition according to the definition you can write, then for all n greater than or equal to m, modulus of 3n minus 1 by 4n plus 5 minus 3 by 4 which modulus is less than epsilon, which implies limit 3n minus 1 by 4n plus 5 as n tends to 3 by 1. Just you remember here, you apply the definition and you write this an minus l with modulus is less than epsilon for every n greater than equal to m. Then you write replace an by, you have to replace and simplify the expression in the modulus and don't simplify the denominator, you keep denominator as it is. Now you keep n one side remaining on the other side, whether you take reciprocal or you take the negative sign, whatever it may be, just you have to get n one side and the remaining other side. After getting that, you replace n by m and you write here, then for all n greater than or equal to m, the same definition you can add there. Okay, an minus l with minus less than epsilon, replace n by this, l by this, and this is the same thing you can add as limit an as n tends to equal to l, you can write the same you are running. So not doing any simplification. If you are doing, you are finding the value of n and you are replacing here. Okay, that's it. Okay. I think there is no need to take all of them here. Third one, fourth one, fifth one, etc. That one here. They are still the same way. Now we'll go for the, you see the syllabus there, you got there you got here sequences. After that you have convergent, divergent, and oscillatory sequences. There are three types of sequences are there. One is the convergent sequence, second one is the divergent sequence, third one is oscillatory sequences. Okay, here you see already you convergence of the function, divergence of a function. Okay, oscillatory of a function also, you know that the same just to see here the same you're defining for the sequences. It's the nth term, that is an. Okay, now you see the convergent sequence. Okay, here you see convergent sequence. A sequence an is said to be convergent. A sequence an is said to be convergent if the sequence tends to a unique part quantity, say L. Okay, an is convergent, sequence an is convergent if the sequence tends to a unique part quantity, say L. That means the meaning of this is so and so. If you see here, in this case, an converges to L. An converges to L. Okay, that is limit an as n tends to equal to L. This is the condition. Okay, convergent sequence means you have to get L is a finite unique quantity. Finite unique quantity you have to get. That must be one and only one unique in a sense. Now there are no other option, that is called a unique. Here you see an is the given sequence. You are taking the limit an and as n tends to infinity. If it is simplified, then you are going to get L that is equal to some quantity, whatever it may be, K, L, constants or whatever it may be, you are getting the some value that is some value, then you can say that is a convergent sequence. Okay. Here also you can correlate with the previous one. You see what are taken the limit of the sequence are taken there. You see here the sequence an is set to converge to L if for any epsilon then there is a positive integer m depending on epsilon such that modulus of n minus L less than epsilon forever. And you see the same definition what are taken in case of the limit of the sequence just now you are taken there. The same you are writing here. You see here the limit of the sequence is what you are taken the same you are writing. And here you see you are taking here limit an as n tends to be equal to L. The same you are writing here. By writing this, you can write this is provided that is you can obvious you can write limit an as n tends to infinity equal to L. You can write. Okay. Now here this is the same you can write as modulus of n minus L. You are taken in the note. You see that note there. There you got this. The same you are writing here. L minus epsilon. Of course, here you can write an belongs to the open interval L minus epsilon comma L plus epsilon. That is the way you are writing here. Okay, now you got here limit an as n tends to infinity equal to L, that is some finite quantity, then you can say the sequence an is the convergent sequence. Now we will move for the next one, that is you take here you see some of the examples. The sequence an equal to 1 by n is convergent. Why it is convergent? Already taken limit an here an equal to 1 by n is there. You see you compare these two flower brackets here, so n equal to 1 by n you are getting. That is the nth term of the sequence. Based on the nth term only we are going to find out the convergence of the sequence. Okay, you see here 1 by n you are getting an and limit an as n tends to infinity. You have to replace n by infinity, 1 by infinity equal to 0. It is not 1 by 1 infinity, limit as n tends to infinity, so you can write n by, you can replace by infinity 1 by infinity 0. Now similarly here also you see the second one example, n by n plus 1 is there. You can write limit an as n tends to infinity equal to limit n by n, numerator keep as it is, but in the denominator you take n as common and you write here, if you take n as common from the denominator you get 1 plus 1 by n. This n get cancels. And if you replace n by infinity, you are going to get 1 divided with 1 plus 0 you are getting. Because here 1 by infinity is 0, 1 plus 0 is 1, and 1 by 1 into 1 that is equal to 1 you are getting. What you are taken in the convergence sequence definition? Here you see what in the first case you got 0. Here you got 1. That means what are they? They are the finite and unique quantity. Is it not? There are no other. Here you can write only one value, that is the unique one is existing. Therefore, you can say those two sequences are the convergence. That is 1 by n is one convergent sequence, n by n plus 1 is another convergent sequence. Okay, that is you are getting two sequences as a convergence by taking limit as n as n is equal to L. Okay. Of course, here then the first case L equal to 0, in the second case L equal to 1. Now we will move for the divergent sequence. First one is the convergent sequence, now the divergent sequence. Okay. Now you see here a sequence an is set to diverge to plus infinity if given any positive real number k, given any positive real number k, However large, there exists a positive integer m depending on k such that an greater than k for every n greater than or equal to m. The meaning of this is here, this is how to write. An is set to infinity, but you see there are plus infinity is different from minus infinity. You see here an is set to plus infinity for a given number, positive real number k, however large, there exists a positive integer m. You see in the previous case, the w array, however small you are taking that, but here you are however large, there exists a positive integer m. There you are written depending on epsilon you are written there, but here you are depending on k you are adding. In case of limit of the sequence, you see there. Here you are writing depending on k you are adding, there you are written depending on epsilon. Now, so that n greater than k for every n greater than or equal to m. The same you can write as here limit an as n tends to infinity equal to plus infinity. This is the definition of the divergent sequence. Okay. Either you can write limit an as n tends to infinity equal to plus infinity. That is an tends to infinity as n tends to infinity. Okay. Now the definition second one. Okay. The same divergent convergence sequence, the same divergent sequence as another definition. A sequence an is said to diverge to minus infinity if given any positive real number k, however large, there exists a positive integer m depending on k such that an less than minus k for every n greater than or equal to m. Here also the same you got to take in case of the previous case. There you got the plus infinity, here you are getting minus infinity, everything is same. Yet you are adding here an less than minus k. That is you are adding in the previous case you are adding n greater than k, but here you are adding an less than minus k, and here you see limit an as n is equal to plus infinity, you are adding in the definition one, but here you are adding limit an as n is equal to minus infinity, you are adding here minus infinity, that is an tends to minus infinity as n tends to infinity. Now, equivalently, the sequence an is set to minus infinity if given any negative real number k, however small, there is a positive integer m depending on k such that a less than k for every n greater than or equal to m. That is an tends to infinity or an tends to minus infinity. Then you can say that is the divergent sequence. That is the divergent sequence. If you remember here, limit an as n equal to plus infinity, means you can get uh, plus infinity or minus infinity, you are going to get the divergent sequence. Okay. Now you see some of the examples here. The sequences n on n square diverges to infinity. How you are writing this? You see already you know based on an you are going to just decide this is whether convergent or divergent. Now just to see here the first one, if you there are these are two problems, not the single one. You see n is there in the on the problem bracket. That is sequence n equal to n here. Here sequence n equal to n square. Okay. Now what how to do? You have to find out the limit. Okay, limit an as n tends to infinity equal to limit n equal to n, limit infinity as n tends to infinity. You are going to get infinity. That is plus infinity. You are going to get. Similarly, here also limit n square as n tends to infinity, that is limit n as n tends to infinity equal to limit n square as n tends to infinity equal to infinity square you are getting, that is again infinity. That's why the n and n square are diverges. So already have taken their limit an as n tends to plus infinity, then you are saying that is a divergent case, or it is minus infinity, then you are saying divergent case. You see the second one here, if you are writing minus n and minus n square, here also the same way, these two are diverges to minus infinity. How it means you see again the same case, that is you have to take what limit an as n tends to infinity equal to limit an equal to minus n in the first case, limit minus n as n tends to equal to minus infinity you are getting. Similarly here limit an as n tends to infinity equal to limit minus n square as n tends to infinity, that is equal to minus infinity you are getting here. Okay. Now here you see one problem here. So that log 1 by n diverges to minus infinity. Log 1 by n diverges to minus infinity. You see for k greater than 0, m belongs to n such that log 1 by n less than log 1 by n less than minus k for every n greater than equal to m. Here you have to find out all time probability, whatever way the case we are using the definition is, you have to find out the value of n here. It is one way or another way. Okay, you see here minus infinity means you can write here log 1 by n less than minus k. You see which definition are taken there. Just to see here, so they are taken definition number 2. The first one they are taken. There are two definitions, plus infinity, minus infinity. Here you got first one is the plus infinity, second one is the minus infinity. Here or they are taken. You see here, an less than minus k is there. This is they are taken here. Okay, that is divergent sequence. Definition number 2 they are taken there. Now you see the same by using that you can write log 1 by n less than minus k for every n greater than or equal to m you can write. Now the same you can write as here minus log 1 by n. You see I'm already told you whenever you are taking the minus sign on both sides or reciprocal the inequality changes. We are taking the minus sign on both sides, that's why we are getting here greater than. This is same for all for every n greater than or equal to m. That is not it is understood okay n greater than or equal to m. Now the same you can write log 1 by n to the power minus 1 because you see log m log a you can write as log a to the power m you can write the same way. So writing here minus in the sense minus 1 is there, minus 1 means log 1 by n to the power minus 1 greater than k. Okay. Now here you take 1 by n to the power minus 1 you can write as 1 by n you can write as equal to log n you are getting here because a to the power minus n you can write as 1 by a to the power n. By using that here you can write 1 by n is equal to you are going to get n here. Okay, log n greater than k is going the same. And here you take exponential of that. Here you take the exponential of the both things. You write here because you have to get the value of n here. You take exponential so that you are going to get e to the power log n greater than e to the power k. Okay. Now after getting that, you take already you know e to the power log x you can write as equal to x you can write. Here also you can write e to the power log n you can write as n. The remaining is same you're writing. Just you replace n by m here and you write here. For if the value n equal to m, then m greater than e to the power k and log 1 by n less than minus k holds. Just you are using the definition number 2 in the divergence sequence and you are getting this value. This is how to remember here. That is the definition for k greater than 0, m belongs to n. Here you can write log 1 by n less than minus k. You can write there. Okay. Now convergence sequence is over. Divergent sequence is over. Now the oscillatory sequences. The oscillatory sequences, the third type. The first one is limit En as n tends to infinity is equal to L. L is a finite quantity, then you are getting the convergent sequence. If limit En as n tends to infinity equal to plus infinity or minus infinity, you are getting the divergent sequence. Now the third type is oscillatory sequences. A sequence n is said to be oscillatory if it is neither convergent nor diverges to plus infinity or minus infinity. Oscillatory sequences are of two types. That is, other than convergent and divergent is there. That is the oscillatory sequence. Oscillatory sequences are two types. The first type is here you see a bounded sequence which does not converge is said to oscillate finitely. That means sequence is not converging, but it oscillates finitely. Okay. Just to see here, you will take the example so that you can get the idea here. Sequence n equal to minus 1 to the power n is a bounded sequence because why it is bounded sequence? It is bounded above as well as bounded below. Then only you can say that is a bounded sequence. Okay. Already are taken in the previous cases. We refer the examples there. You got supremum is equal to plus 1, infimum is equal to minus 1 you got there. That means you can write minus 1 less than or equal to an less than or equal to 1 you can write. Okay, or you can say minus 1 less than or equal to an less than or equal to n you can write. Now to see limit a to n as n tends to infinity equal to you can write minus 1 to the power n means you compare these two here. Okay, remove the power brackets n equal to minus 1 to the power n you are getting here. Now limit n as n tends to infinity equal to you replace n by 2n, replace n by 2n, you are going to get here minus 1 to the power 2n that is equal to 1. Okay.